Hey everyone, Mr. Newman here. We're going to do a lot of things involving graphs of functions, and there's actually a whole lot of stuff in here. Hopefully most of it's review. If anything isn't, we'll go over that and we talk about it in class. So let's get started. First of all, we want to talk about describing functions. There are a handful of words that we use that are usually related to the graphs. For example, if you talk about increasing, that means as the input increases, the output should increase. In other words, if the x increases, the y should increase, and this always on the graph looks like going up whenever you're going to the right. So on our example here, you see the interval from A to B is an increase, from C to D, that part is an increase, and from E to F, that is an increase. Down on the bottom graph here, oh, and by the way, these big circles, don't draw these yet. You can wait on drawing them till the end because we're gonna erase them, and then I'm gonna just circle the decreases for you as well so you can see them all. On the bottom here, you see that's an increasing, even though the arrow is pointing down. If you consider as you're going to the right, as input is increasing, as x is increasing, the value of that is increasing, the y value, the output is increasing. So don't be too confused by that arrow. It's kind of picture walking to the right. That graph is going to go up as you're going to the right. So that part's increasing, and we name that as anything less than x is less than -3. Often when talking about what section of the graph is increasing or decreasing, we use x because we want to use the domain. If we used the y instead, we could talk about multiple parts of the graph, but as long as this is a function, which it is, then the x should be very specific to one part of the graph. So that is the interval x is less than -3. It is also increasing from here to there, and so we're going from 1 to 4, so 1 is less than x, which is less than 4, is the way we name that interval. So that's the increasing parts, so we erase all that. For decreasing, if the input is going up, and the x value is going up, and that means the output is decreasing, the y value is decreasing. And that always looks like going down as you're going to the right. So those are our two options. Up and to the right is increasing, down to the right is decreasing. The interval from B to C on that top graph is an example of a decreasing part of the graph. And then also from D to E is another part that is decreasing. The interval on the bottom graph is from -3 all the way to 1, and that is how you write that. Just real quick comment about interval notation. Some of you guys have been using, or I've seen this as well. That's perfectly fine. I don't like this quite as much because it looks like a point to me. Looks like the point -3, 1. So you always need to know what context you're talking about when using that, and be careful with that. Likewise, that's strictly less than if you have or equal to, then you need to have brackets like that. Okay, so that's interval notation there. So coming on down, next thing is a constant. That's if the input is increasing or the x value is increasing, then the output or the y value is staying the same. So constant functions are always horizontal. The only example we have there is all the way to the right. That is when x is greater than 4 on that graph. All right, local minimums have a very specific definition. Any nearby output is greater than or equal to, I should include. And examples of that, this is a local minimum. That means if you go to the left or to the right, everything around that is going to be, around the point of A, is going to be bigger. And we're kind of assuming that the function does not continue on to the left, but only goes to the right. And as you see, that's a local minimum. C is the lowest value there. So anything around C, if you go to the left or to the right, gets a little bit bigger than C. And E is also a local minimum. E is actually also the absolute minimum because it is the lowest on the whole graph that the whole graph gets. All right, down on the bottom graph, we have the value x equals 1. That output is the local minimum, but it is not an absolute minimum. And the reason for that is because if you look over there to the left, the graph does get lower. Now, that arrow means that it keeps going, so that means that there's actually no absolute minimum on this graph, and that can often happen. So we have a relative minimum, not an absolute minimum. Local maximum is any nearby output is less than it. So, for example, B is a local maximum because if you go to the left or to the right at all, those values decrease and are less than that. D and F are the other local maximums, and this is a special case because we have two absolute maximums, and that can happen. In fact, you can have an infinite number. So B and F are both absolute maximums. Over here on the bottom graph, we actually have an example of that. All of those are absolute maximums. So they're local maximums, but they're also absolute maximums. I think our book, one thing you'll see is you might also see relative maximum or relative extrema. So that's another word that can replace local. Now, so that's x is greater than or equal to 4 is the absolute maximum, is the range of the absolute maximums there. So let's see here. Interval notation of this real quick I want to talk about. 4 is bracketed because it could be equal to 4, but we put a parentheses around the infinity symbol always because instead of a bracket, and that's because you can't actually equal infinity. Infinity is a concept, not a number, and so you always are less than infinity, not less than or equal to. So make sure that's like that. Now, x-intercepts are known as the zeros. That's where the graph intersects the x-axis, okay? Now, where f of x equals 0. That's why we call it a 0, but you have to be careful because the y-intercepts where the graph intersects the y-axis, and that's where x equals 0. Those are not known as zeros. So only the x-intercepts, only where the output is equal to 0, are known as zeros. So that's kind of a funny way of saying that, but that's how they talk about that, okay? So speaking of zeros, you can always look on a graph and see where the zeros are. I'm just going to circle them real quick on this graph. 1, 2, 3 on that bottom graph there. You see where they intersect the x-axis. So pulling out your graphing calculator or using Desmos is always a good way to check the zeros. However, we also need to be able to find those algebraically. And like we said, that's when f of x equals 0, so is equal to 0. So the way we're going to solve that is simply setting the function equal to 0. So you see I replaced f of x with 0 because we just want to know for what x value do I plug in, do I get out a 0. So let's solve this. I think one thing I'm not going to worry too much about quite yet is factoring that. You should have remembered that from last year, but we're definitely going to practice that later this semester. So you can factor that, and whenever two things multiply to equal 0, one or the other has to be equal to 0. So 3x minus 5 equals 0, or x plus 2 is equal to 0. Let's take the latter case first. That solve for that, x equals negative 2 is one option, or if we solve for this, x is 5/3. So if you plug in either of those up there, you should get out a 0, and that's actually how we're going to check our work real quick. Let's check by plugging in negative 2, and when you plug in negative 2, you get 12 minus 12, which is 0, so that checks out. You could do the same thing with 5/3. I'll let you do that on your own time, but that's just a good practice, a good habit to check those. All right, so those are the two answers. Let's go on to the next one. We have the square root of 10 minus x squared. I want to substitute in a 0. Say, okay, when is the output equal to 0? Let's square both sides, and then let's solve for that. One thing to remember, when you take a square root of both sides, you've got to put plus or minus, because that means there's more than one possible solution. X equals plus or minus the square root of 10. It is perfectly fine to answer in that way. I just want to show for people who haven't seen that notation before, that means x can be the square root of 10, or x can be negative square root of 10. Either of those are both answers you must have, and you must write both when you're answering this. All right, let's go to the third one. Again, we're going to set it equal to 0. This time I'm going to multiply both sides by the denominator. We can do that. I don't like the phrase cancel out, and we'll talk about more of that in class later, but basically t plus 5 divided by t plus 5 equals 1, and 1 times anything keeps that thing the same, so that is why I say those two divide out, and we get on the left there, anything times 0 equals 0, so 0 equals 2t minus 3. Solve for t, and we get t is 3/2, and that is the answer for that one. So you see, finding the zeros of functions, fairly straightforward. Set it equal to 0 and solve. Next up, we want to find the average rate of change, and the phrase average rate of change is simply another way of saying the slope, or rate of change is slope. Average rate of change kind of ignores everything in between. So you're going to see what we always are talking about or looking for is 2 points and finding the slope between these 2 points. We have the x values of the points, we just need to find the y values, or the outputs. So let's go ahead and plug in -2 from the first point, and we get out the output of that is also -2. So the first point is -2, -2. You can see that over there on the graph to the right. I just highlighted it right there. So we could have just looked at the graph and plotted that, but we want to make sure it's exactly -2, and we just show that it is. Let's find the other point. We notice the input is 0, and the output also happens to be 0, so that happens to be 0, 0, and I just drew that point in. So the average rate of change is going to be the slope between those 2 points. So I could draw a line, and it looks like it's going to be a slope of 1. Let's just make sure with our formula for slope, we subtract the difference between the y's and divide by the difference between the x's, and we get 2/2, which is 1. So the average rate of change from from -2 to 0 is 1 for this function. Go ahead, I want you to try applying this to the next problem. Try that on your own, and we're going to bring that into class. Excuse me. Also graph that on the graph there on the right so that you can compare that to your classmates' answers there as well. All right. Last thing, even and odd functions. The definition of an even function is simply that if you plug in the opposite as an input, that is the same as if you plug in the regular number. For example, f of -3 is equal to f of 3 in an even function. F of 10 is equal to f of -10, okay? So first I want to show you some examples. This happens when y equals x squared. So if you plug in 5 squared is 25. If you plug in -5, you also get positive 25. So plugging in the positive and negative of a number always gets you the same number. Same happens for x to the 4th and x to the 6th, and any combination of these. You could say x to the 6th minus x squared, or you could also say y equals 3x to the 10th. So I think you guys can see why they call these even functions. It does not have anything to do with the coefficient. You see how 3 is the coefficient, but it's the powers or the exponents that are all even. And as long as they are all even, doesn't matter whether you're adding or subtracting them, and whatever numbers you're multiplying them by, they will always give you an even function. Another function that we're going to look at later in the semester is cosine of x. That's a trig function that's even. And the absolute value function is also even, because if you plug in absolute value of -2 and the absolute value of 2 are the same. All right, I'm just going to give you a random example, and we're going to talk about this a little bit later. That is an even function, and I'll tell you how you can figure that out from the graph in just a moment. But let's look at odd functions. Odd functions are a little bit different. When you plug in a negative input instead of the value, you get out the opposite of that. So for example, if you plug in -5 and got out 10, then that means if you plug in 5, you should get out -10. Okay, it's a little bit tricky and a little bit confusing, but let's look at some examples and I can explain a little better. So the first odd functions we have are just lines. Those are a little bit boring, but you notice here we also have x to the 3rd and x to the 5th are odd functions, as well as x to the 5th minus x to the 3rd. And even 8x to the 15th. So once again, it's only the exponents that have to be an odd number, and as long as they all are, then we're good to go. Then you have an odd function. Right here, this also has an odd exponent because it can be considered x to the 1st. That's the same as just y equals x, so that's why those are still odd. We've also got sine of x in there, and I'm going to graph one of these for you real quick. You notice there is a different kind of symmetry as on the left side. On the left, it's always, even functions are always symmetric over the y-axis. The reason for that being is that inputs that are equidistant from the y-axis will give you the same output. Odd functions, however, have a rotation, are rotationally symmetric. In other words, it's 180 degrees. If you rotate that thing 180 degrees, then you will end up back in the same spot. Another way to think about that, you could also think of it as a reflection over the x-axis and then the y-axis. the order of that doesn't matter. You could reflect over the y-axis first and then the x-axis. All right, a little bit longer video. Thank you guys for watching, and we'll see you in class.